All right, so what I'm going to do through the next of this packet is I'm not going to go over all of it. I'm just going to hit the parts that I think you need to know conceptually for your test. I'll put Faribagh's video if you want to go into it in more detail, but I think what I'm going to tell you will be sufficient for the conceptual part of this. Now, when we looked at the other cell systems, we had two metals. And what drove the electrons, right, was we had the anode here and the cathode here. And that potential difference drove the electrons. You can do the same thing with using the same metal, only use concentration as a gradient. So think of it this way. I've got a dilute solution here of nickel and a concentrated solution here. What's going to happen is the dilute, this is dilute and this is concentrated, so it's going to want to equilibrate. This is not at equilibrium. So nickel Ni pluses are going to pop off here, so I'm still going to get reduction, and that will help add more Ni2 pluses, because this is more dilute. It wants to be more like this. I'm going to get more of my anions will come over here to balance the charge, and the concentration here will go up. Then on this side, the extra Ni2 pluses will go onto the electrode. I'll still, as normal, sorry, this is oxidation, not reduction. This will still be reduction. These Ni pluses will go on the electrode. They'll go out of solution, which will decrease this concentration. And eventually, it will equilibrate. So as normal, at my anode, I'm going to get oxidation. At my cathode, I'm going to get reduction, but it is driven by this equilibration of the concentrations, with dilute being over here and concentrated here. So this is a concentration gradient. The half cell containing the dilute solution, you'll have oxidation. And the half cell containing the concentrated solution, you'll have reduction. Okay. Now what we're going to look at is section 20.9 and electrolysis. All right. Now, galvanic cells are based on spontaneous or favorable redox reactions. And students have asked me this. They said, could we force the reaction to go the other direction? And yes, you can. You can apply electrical energy. But again, spontaneous means it goes unassisted. We're assisting. We're assisting. So we're going to look at a molten salt situation where we've got sodium and chlorine. And our reduction reaction is going to be, and this is not normally favorable, we're going to have to put some energy in to do this. And at our anode, we're going to, remember, we're going from a negative now to neutral, so that is in the oxidation direction. We're actually going to make chlorine from sodium chloride. This process is called electroplating. And we can measure the quantity of electrons or the quantity of charge passing through this in terms of coulombs. All right. Now, if you look at your chart, this is our last equation. I am looking at my charge, my time, and my current. And by using these values, I can actually determine how much electroplating I'm going to get, or how much mass I'm going to get on that electrode. Now the way electroplating works, and this is just a very basic diagram. All right, so this is going to be my anode, and this is going to be my cathode. I don't think Faribault talks about this, oops, but I'm going to do this. So I'm doing a problem up here with aluminum chloride. What's going to happen here is that on the anode side, I'm going to take the aluminum chloride that's normally a solid, and I'm going to make it a liquid by melting it. It's going to be molten aluminum chloride. That allows it to flow. Now, here at my anode, I've got these negative chlorine ions. And what's going to happen is they are going to undergo oxidation. A minus to a neutral is oxidation. And that's going to cause the electrons to flow on the wire. Now, on this side, aluminum ions are going to come up here. They're going to snatch those electrons like they always do, and I'm going to get aluminum solid. And that aluminum solid is going to plate. It's going to set here, that solid, just like it always does. Now, on the AP test, what they want you to be able to do in these systems is they want you to be able to talk about how much aluminum would plate in this spot. Now, here's where units become really important. So what we're going to do is we're going to go from, I've got an hour. That's really my given. 60 minutes is my given. And I'm going to go from hours to grams. Now, I'm going to show you how we're going to do this. Now, this equation here, I is equal to charge divided by time. That is in your formula chart. Now, I is current in amps, Q is charge in coulombs, and T is time. It's going to be in seconds. So we're going to take our minutes first, and we're going to convert it to seconds. Now, it says here that I have 10 amps. That is basically, an amp is equal to a coulomb per second. So what that means is that for every 1 second, I have 10 coulombs. So this value here is going to get me from time to coulombs. All right. Now, I'm going to go, I need to get to moles and then to grams. So what I'm going to do is I'm going to drop coulombs and I'm going to go to mole electrons. Now, what was that again? That is going to be F. F is 96,485 coulombs per mole. That's in your formula chart, remember? F is coulombs per mole. So, I'm going to put that here. This is important because this is the conversion that I'm going to use. Now, the next part is particularly important. When I went, oh sorry, this should be 3 electrons, sorry about that. When I went from aluminum 3 plus to aluminum, how many moles of electrons did I use? In this case, with the metal, I used 3 moles. So what that means is that this is going to be per 1 mole, but 3 moles of electrons for every 1 mole of aluminum that I make, right? Because that is what I did here. And so then I'm going to multiply that by 1 mole of aluminum. I wish I could do this all in one, but I got is 26.98 grams aluminum, and so that's going to be 3.36 grams. So where are my important steps here? So I'm going to put this, I need another. let's look at our 3 important steps. We're going from time to mass. I've got my time. I need to make sure it's in seconds. I can convert seconds to coulombs using amps. I can convert coulombs to moles of electrons using F. I can convert moles of electrons to moles of aluminum using my equation. And then I go from moles to grams using molar mass. All right? Let's try another one in the opposite direction. So this one says, how many minutes would it take for 1.75 grams of aluminum to be produced? All right, so let's go the opposite direction. Now I've got 1.75 grams of aluminum. I'm going to drop 26.98 grams is 1 of aluminum, is 1 mole of aluminum. 1 mole of aluminum is how many? 3 moles of electrons. So now I've gone from the quantity to electrons. Now I can go from electrons. 1 mole of electrons is 96485 coulombs. I can go from 10 coulombs per 1 second because I still am at 10 amps. And I need to convert seconds to 1 minute because it asks for minutes, and that equals 31.3 minutes. So again, we're using amps to get to time to get to coulombs through our amp. Then we are doing coulombs to moles to get there. And then last but not least, we've got our mole electroplating through that oxidation reduction. So really, when you start looking at these, the way that I want you to tackle these problems, going from time to mass or mass to time of the material that deposits on here, I want you to think of this as a conversion factor, and that will allow you to go from moles of electrons to your electrical unit to do it. Those are tricky problems, but you're going to get some practice with that on your OWL, and you're also going to get some practice with that on your progress check.